morning, everyone. Our first speaker for today is Rasmus. Um, my timer is speaking to me. You have 10 more seconds. And he's going to talk about approximate Gaussian elimination for Laplacians.
All right. Hi. Um, yes, I'm going to tell you about approximate Gaussian elimination for Laplacians. This is joint work with Sushant Sachdeva. We're interested in solving linear systems of equations. That means given a matrix A and a vector B, we want to find a vector x such that Ax equals B. It's a problem that we often need to solve, both in theory and in practice. But unfortunately, standard algorithms for this are too slow to handle large matrices. Now, in a major result in 2004, Spielman and Tang showed that if your matrix A is a Laplacian matrix, then you can solve linear systems in A in nearly linear time, approximately though. And for this, they won the Gödel Prize in 2015. Okay, so today you'll see that we can solve Laplacian linear systems via a new algorithm that we call approximate Gaussian elimination. It's a very fast and simple algorithm with provable guarantees. It can also be extended to new classes of matrices, although we don't have time to focus on that today. Okay, so classically, how might you solve a linear system? You could do Gaussian elimination. That takes you order n cubed time for an n by n matrix A. You can do faster. You can do n power omega time, where omega is the matrix multiplication constant, which is approximately 2.37. But when A is a Laplacian matrix with m non-zeros, you can solve approximately in A in nearly m square root log n time. It's shown by Cohen, myself, and others in 2014, and it's the fastest currently known Laplacian solver. There have been lots of applications of Laplacian solvers, including solving partial differential equations numerically via the finite element method, using them in interior point methods for optimization, doing learning on graphs, getting faster flow algorithms, and more. There have also been many papers just improving the Laplacian solver, making it simpler, making it faster, and making it parallelizable. So this is a very active area of research. Okay, so what are Laplacian matrices? A Laplacian is a symmetric matrix L, where all the off-diagonals are non-positive. And for every row, the diagonal entry of that row is exactly equal to the sum of the absolute values of the off-diagonals in that row. Laplacians also correspond to weighted undirected graphs. So for every vertex in our graph, we'll associate that vertex with a row and a column in our matrix. And then edges in our graph will give us entries in that matrix. So an unweighted edge between vertices 1 and 2 will give us a 1 in the diagonal for vertex 1, a 1 in the diagonal for vertex 2, and a -1 in the 1, 2 off diagonals. If we have more edges, we get the Laplacian of the whole graph by just summing together the Laplacians of the edges. Okay, so it's a symmetric n by n matrix. It corresponds to this weighted undirected graph G with vertices V, edges E, and edge weights W. We'll say that there are n vertices, m edges, and W assigns a positive weight to every edge. We can then also think of the Laplacian as related to the weighted adjacency matrix of the graph. So L is equal to D minus A, where D is the diagonal matrix of weighted degrees in the graph, and A is the weighted adjacency matrix of the graph. The Laplacian also has a very nice quadratic form. X transpose Lx is equal to the weighted sum over edges of the square of the difference in x across that edge. Notice that that's never negative. So this is a non-negative quadratic form. So what do we show about Laplacians? We show that you can epsilon approximately solve linear systems in Laplacians in m log cubed n log 1 over epsilon time. But something like this was already known. The real point is that we give an incredibly simple algorithm that achieves this. And our algorithm is based on our second theorem, which says that you can compute a sparse approximate Cholesky factorization of a Laplacian in m log cubed n time. So approximate Cholesky factorization, that's just Gaussian elimination, what we call it when we do it to a PSD matrix. And when we have this approximate Cholesky factorization, it'll then be very easy to solve linear systems. These notions of approximation that I'm talking about, we'll get to those, but they are the standard ones used in solver papers. Okay, so to review a few things about positive semi-definite matrices. So a matrix A is positive semi-definite if it's symmetric and the quadratic form x transpose AX is non-negative for all x. So we already saw that Laplacian matrices are positive semi-definite. For any PSD matrix, we can define a natural semi-norm. The A norm of x is just the square root of x transpose AX. This can then be used to introduce a useful notion of approximately solving a linear system. So say we want to solve AX equals B. We say we have an epsilon approximate solution if we can find x tilde such that the A norm of x tilde minus x is less than epsilon times the A norm of x. X is the true solution. Recall that A norm is just the square root of the quadratic form. This is the right norm for most applications because it also tells us that we've found an approximate minimizer of the quadratic form. Okay, so we saw a notion of approximately solving a linear system. Now we want to talk about approximating PSD matrices. So we'll say that two PSD matrices, A and B, are epsilon approximately equal if for all vectors x, x transpose AX, the quadratic form in A, is less than 1 plus epsilon times the quadratic form in B. And also the other way around. The quadratic form in B is less than 1 plus epsilon times the quadratic form in A. Then we'll say the matrices are approximately equal. Now there's a very nice connection about this first concept of approximately solving a linear system and the second of approximating a PSD matrix. You can see this through a very simple algorithm called preconditioned iterative refinement. This says if you want to solve AX equals B approximately, you can do that by finding a preconditioner matrix C that should be easy to invert and be a good approximation of A in the sense we just saw. So a 1/2 approximation of A. Then consider the equivalent linear system, C inverse AX equals C inverse B. So we just multiplied by C inverse on both sides. But now you can solve this by just iterative refinement. Guess and refine a few times. So we'll start by guessing a vector, a solution vector that's just all zeros, and then we'll update a few times by xi plus 1 is xi minus the residual C inverse AXI minus C inverse B. Now if you do that log 1 over epsilon times, you get an epsilon approximate solution. So this is how we can get approximate solutions. Okay, now I just want to remind you, how can we exactly solve a PSD linear system? So the standard approach is Cholesky factorization. It says find an upper triangular matrix such that U transpose U is equal to A. Then we can just set X equal to U inverse U transpose inverse B. But these inverses are easy to apply because it's easy to apply or to solve in upper and lower triangular matrices. That's just a homework exercise to do that in time proportional to the number of non-zeros in the matrix. Okay, now we introduce a notion that we call proximate Cholesky factorization. It says find U that's upper triangular such that U transpose U is 1/2 approximately equal to A. And then if you have this, you can use it as a preconditioner in preconditioned iterative refinement, and this will then give you a good solution in log 1 over epsilon iterative refinement steps. Okay, so what do we show? Let's go back to our theorem about these approximate Cholesky factorizations again. We show for any Laplacian L, you can compute an upper triangular matrix U such that U transpose U is 1/2 approximately equal to L. U only has m log cubed n entries, so it's still pretty sparse. And the running time is m log cubed n. So we get it quite fast. The next thing I want to do is to review Cholesky factorization. This is an algorithm that you've probably all been taught. But when you're taught it in a textbook, the standard view is additive. So we see the algorithm as producing a sequence of products of matrices. Now I want to instead look at it, sorry, the standard view is multiplicative. We see it as producing a sequence of products of matrices. Now I want to take an additive view of the algorithm instead. So rather than a sequence of products, we'll think about it producing a sequence of sums of matrices. So why take this additive view? The additive view combines well with concentration results for sums of random matrices. And we understand sums of random matrices much better than we understand products of random matrices. And so this turns out to be helpful when you want to change the algorithm. So let's do Cholesky factorization. We have a PSD matrix A, and you've all checked its PSD, so let's start. Let's find the rank 1 matrix that agrees with A on the first row and column. So here I'm showing you the first row and column. Here's a rank 1 matrix that agrees with that row and column. Now, let's subtract this rank 1 matrix from our current matrix. We get zeros in the first row and column. Now what's left, and we say we've eliminated the first variable. What's left is PSD again. So we can repeat. Find the matrix, the rank 1 matrix that agrees with our current matrix on the next row and column. Here's that rank 1 matrix. Now let's subtract the rank 1 matrix. Now we have zeros in the first and second row. And of course we can repeat this, and we say we've eliminated the second variable. We can repeat this until all parts are written as rank 1 terms. So here's A written as a sum of rank 1 terms. Notice a special structure. The second term is non-zero only from the second entry onwards. The third term is non-zero only from the third entry onwards, and so on. This means that we can write this as a product of a lower triangular matrix and an upper triangular matrix. And in fact, this is our U transpose U. So we got our Cholesky factorization. But we also saw it as producing a sequence of sums of matrices. Okay, so what's special about doing Cholesky factorization on Laplacians? The remaining matrix is always a Laplacian after we take out some PSD rank 1 terms. So here is a Laplacian matrix. Let's write it as a sum of a rank 1 term that agrees with the first row and column, and then a remaining matrix. So here we have rank 1 term on the left. On the right, we have the remaining matrix. The remaining matrix is a new Laplacian, and this will always be true. This is going to be extremely helpful because we know a lot about how to approximate Laplacian matrices. Okay, so why is Cholesky factorization slow? Cholesky factorization for solving a Laplacian Lx equals b can take order n cubed time, even when the original matrix is sparse. For example, this happens with the Laplacian of an expander graph. Okay, the main issue is what's called fill. So let's see that. So we have a Laplacian L. We want to eliminate a variable v. I'm showing you the corresponding vertex v in the graph. Okay, when we eliminate v, we remove the edges incident on v. Then in our new graph, we get a clique on the neighbors of v. This is how the algorithm ends up being slow because we're adding in all these dense matrices that will quickly make the degrees blow up. And so we end up eliminating in a very dense matrix. So elimination creates a clique on v. But there's hope because that clique can be sparsified. Laplacian cliques can be sparsified. So we could hope to replace this clique with an approximate version that's sparse, while still ensuring that our new matrix is a good approximation of the old one. And this, in fact, is exactly what we'll do. So just to recap Cholesky factorization, it's pick a vertex to eliminate, add the clique created by eliminating v, and repeat until you're done. Okay, here is our algorithm, approximate Cholesky factorization. It says pick a random vertex to eliminate. Now sample the clique created by eliminating v, and repeat until you're done. And that's it. We'll need to see how to do the sampling. That'll be next. But first, I just want to mention this resembles a randomized version of a deterministic heuristic algorithm that was very popular in the 80s and 90s for solving these systems, called incomplete Cholesky. But now we can finally analyze this, or something like it. Okay, so let's do the sampling. How do we sample a clique? So let's do an example. We want to eliminate vertex 1. It has neighbors 2 through 5. For each edge from 1 to a neighbor v, we're going to pick another edge from 1 to a neighbor u with probability proportional to the weight of that edge. Then we're going to insert an edge between v and u with weight equal to the product of the original two edge weights divided by the sum of the original two edge weights. So let's see it. We start with the first neighbor, neighbor 2. Pick a random neighbor, say 4. Put an edge between 2 and 4. Then we go to the next neighbor, say 3 here, and then pick a random neighbor 4. Put an edge between 3 and 4. And we keep going until we've got our approximate version of the clique. But we've only put in one edge for every edge that we started with. And now we've seen the whole algorithm. Okay, so what have we done to the running time? In Cholesky factorization, we eliminate n vertices, and each time we add a clique. The running time is on the order of sum over vertices, degree of the vertexes we eliminated squared. This degree squared is the size of that clique that we're adding in. But we're adding in all these dense cliques, so the graph quickly has growing degrees, and this can end up being n cubed. In approximate Cholesky factorization, we instead eliminate n vertices, and each time we add a sparsified clique. This should only take on the order of sum over vertices, degree of the vertexes we eliminated at the time. But now we're not adding these dense matrices anymore, so the degrees are not blowing up. And so this ends up just being m log cubed n. Okay, so how could we prove that something like this works? We want to show that u transpose u is 1/2 approximately equal to L. So the first thing we do is we in fact sure that at every intermediate step of the algorithm, our matrix is equal, so the approximate matrix that we're maintaining is equal in expectation to the original matrix. This of course tells us that the output is also equal in expectation to the Laplacian L. It also means that we're working with a matrix martingale because we're maintaining the expectation throughout. So u transpose u is a matrix martingale. And we use this when we're proving that u is concentrated, or u transpose u is concentrated. So what are the key parts of proving concentration of a matrix? You need that there's low variance in the process. To control the variance, we're crucially using this random elimination ordering. This helps us smooth out the variance of the process across the matrix. So that comes from the random elimination order. Now, the second part we need is small sample norm. This is where a lot of the work comes in many other Laplacian solvers. So the Laplacian solvers typically create a low stretch tree, or they use another graph construct to estimate sample norms. We just start with trivial bounds on the norms of the edges, and then we use a triangle inequality on effective resistances to bound the norms on edges created by elimination. And that's all we need. Okay, so in conclusion, you saw that we can solve Laplacian linear systems via approximate Cholesky factorization. It's a fast, sparse, and simple new algorithm with provable guarantees. And it can also be extended to some new classes of matrices, although we won't talk about that today. Yeah, thank you. So you mean when the matrix is still a Laplacian? Absolutely. I mean, this is a popular heuristic. People do it out in the real world. It's very, very hard to prove that it works. And it works well for M matrices in general, and it breaks down if you have something much worse than that. It doesn't depend on the condition. Well, there's probably like a log in the weights and the precision somewhere, but yeah. Yeah. Yeah, yeah. I don't. I'm not an expert on that sort of thing, but it might be. Although, I mean, right now it's really just randomization that we're using, and figuring out when you might occasionally have made a mistake, which is sort of what we're hiding with the randomness. That's pretty hard. Yeah, yeah. So yeah, but it would be a lot more work.